This video is brought to you by thepuzzler.com. In this video, we look at the 2021 AMC 10A. We will look at each problem, its answer, and a complete explanation of the solution. Without further ado, let's start. A note before we start. For each problem, we will try to look at the most test-taker friendly solution that gets the job done, and disregard the completely rigorous solution except if they happen to be the same. Problem number 1. What is the value of 2 squared minus 2 minus 3 squared minus 3 plus 4 squared minus 4? Let's tackle each term separately to solve this problem. 2 squared gives us 4, 4 minus 2 gives us 2. 3 squared is 9, 9 minus 3 gives us 6. 4 squared is 16, 16 minus 4 gives us 12. So we add up 12, and we get 2 minus 6, negative 4, plus 12, or 12 minus 4, which gives us our answer of 8. Let's do problem number 2 now. Portia's high school has 3 times as many students as Laura's high school. The two high schools have a total of 2,600 students. How many students does Portia's high school have? Let's say Laura's high school has X students. Now X could be any value. Well, Portia's high school has 3 times as many students, or 3 times X. Adding this up will get the total number of students, which is 4X. The problem also tells us that the total number of students is also equal to 2,600. So we can set these two equal, divide both sides by 4 to isolate the X, and 2,600 divided by 4 would give us 650. So our answer would be 650 students. Wrong. We have to multiply by 3 because we're trying to find the number of students in Portia's high school, and this is the number of students in Laura's high school. Multiplying by 3 would give us 3x times 1,800, because 600 times 3 is 1,800, plus 50 times 3, which is 150, which gives us 1,950. Problem number 3. The sum of two natural numbers is 17,408. One of the two numbers is divisible by 10. If the units digit of that number is erased, the other number is obtained. What is the difference of these two numbers? Now, to solve this problem, we have to realize when is a number divisible by 10. Well, if you watched our video on divisibility rules, and you'll find a link to that in the description below, you'll see that a number is only divisible by 10 when it ends with the number 0, or the digit 0. Thus, this bigger number is some number x, and x isn't a digit, it's a number, that ends in 0. Removing that 0, we would get the number x. So our bigger number is x, 0, and how do we add a 0 to a number at the end? We multiply it by 10. So our bigger number is 10x, and our smaller number is x. Adding this up, we get 11x. Now this is equal to 17,402, which the problem tells us. Dividing both sides by 11 to isolate the x, we get 1, 64, 598, 2. Multiplying by 10 to find our bigger number, we get 15,820. Let's now subtract 1,582 from this. We get 10 minus 8, 12 minus 9, 8 minus 6, and 15 minus 1, which gives us 14,238. Problem number 4. Problem number 4. A cart rolls down a hill traveling 5 inches the first second and accelerating so that during each successive 1 second time interval, it travels 7 inches more than during the previous 1 second interval. The cart takes 30 seconds to reach the bottom of the hill. How far in inches does it travel? So during the first second, the cart travels 5 inches. During the second second, the cart travels 5 plus 7 or 12. inches. During the third second, it travels 5 plus 2 times 7. That would be 19 inches if you're keeping track, and so on. Until finally, it travels 5 plus 29 times 7. Notice that this number is not 30 because this 5 is in the first second, and then after that we only have 29 seconds. Now this is just the arithmetic sequence with first term 5 and common difference 7. And to calculate the sum of that, we just apply the formula that we learned about in our arithmetic sequence video. You add the first and the last term. That's 5 plus 29 times 7, or 10 plus 29 times 7. And you multiply by the total number of terms. So this is basically saying that you multiply by the average of the list, 30 times the average of the list. And how do we find the average? Well, we divide this first term by 2. So now calculating that parentheses, 29 times 7 is just the same thing as 30 times 7, 210 minus 7, or 203. 203 plus 10 gives us 213 times 30 divided by 2. So this is 213 times 30 divided by 2, so 213 times 15, or 2130 plus 1065. This gives us an answer of 3195. Let's move on to problem number 5. The quiz score of a class with more than 12 students has a mean of 8. The mean of a collection of 12 of these quizzes is 14. What is the mean of the remaining quiz scores in terms of K? Just to quickly summarize the mean, that's just adding up all the numbers in the list and dividing by the number of terms in the list. So what is the sum of all these quiz scores out of this collection of 12 that we took? Well, if the average is 14 and there's 12 of them, then we can find the total by multiplying 12 times 14, which you might recognize as 13 squared minus 1 as a difference of squares, which would give us 168. Now what's the total sum? The total sum of all the quizzes is 8, which is the mean, times the total number of quizzes, 8K. And since we've subtracted 8K, and since we've subtracted 168 out of that, our new total sum is this. Now we divide by the total number of remaining students. We've already taken 12, so we divide by K minus 12, since that's how many new remaining students we have. And this matches one of the answer choices. It matches B. So we're done. Let's try problem number 6 now. Chunto and Jean start hiking from a trailhead towards a fire tower. Jean is wearing a heavy backpack and walks slower. Chunto starts walking at 4 miles per hour. Halfway to the tower, the trail becomes really steep and Chunto slows down to 2 miles per hour. After reaching the tower, she immediately turns around and descends the steep part of the trail at 3 miles per hour. She meets Jean at the halfway point. What was Jean's average speed in miles per hour until they meet? Well, guys, in this problem, they only tell us about the rates of each person at certain points. But they don't tell us anything about the time it takes them to reach a certain part of the trail or the actual distances. So it's safe to assume the distance of the trail. We can assume that the trail is a distance of 10 miles. And if they start walking at 5 miles per hour, then halfway to the tower, the trail becomes really steep. So if there are 10 total miles, well, when we divide it by 2, half of the track is equal to 5 miles. 5 miles. And Chunto travels 4 miles per hour for that half. So that would take him 5 over 4 hours, which would be 5 over 4 times 60. We don't actually need to convert it to hours, to minutes, but we'll just do that right now to keep it simple. This would give us 5 times 15, or 75. Now for the second half, it's also 5 miles, but this time he's only going at a rate of 2 miles per hour. So 5 times 2 times 60 would give us double the amount, 150, which makes sense. If you're going half as slow, it takes you double the time. Finally, after reaching the tower, she immediately turns around and descends a steep part of the trail at 3 miles per hour. So once again, we're going 5. Remember that she meets Jean at the halfway point, so it's still 5. And 5 divided by 3 times 60 cancels out to give us 100 minutes. So the total amount is 250 plus 75, which is 325. So it takes her 325 minutes. It takes Jean 325 minutes to go 5 miles, since that's the half distance that she went. So we get 5 over x is equal to 325, or that 305 over 325 is equal to x. Now, in this problem, we can multiply by 60 to get our answer, since we're asked to find the miles per hour, not miles per minute. So 5 over 325 times 60. The factor of 5 cancels out from both of the numerators to get 12, and we divide by 25 here to get 1, and that would leave us a remainder of 75, 3. So our speed is just 12 over 13. Note that in this problem, you could have solved it without actually converting to minutes. Depends on your preference. Problem number 7. Tom has a collection of 13 snakes, 4 of which are purple and 5 of which are happy. He observes that all of his happy snakes can add, none of his purple snakes can subtract, and all of his snakes that can't subtract also can't add. So our first thought here is, if the purple snakes can't subtract and snakes that can't subtract can't add, but all happy snakes can add, then maybe all purple snakes are not happy snakes. But let's look at the answer choices. Which of these conclusions can be drawn about Tom's snakes? Purple snakes can add. Well, it says none of his purple snakes can subtract, and they cannot subtract, and snakes that cannot subtract cannot add. It clearly tells us that, so it's not this. Purple snakes are happy. Well, if these purple snakes cannot add, we already established that, and all of his happy snakes can add, well then his purple snakes are not happy. Snakes that can add are purple. Let's see. If I have a snake that can add, but we already established that purple snakes cannot subtract or add, then I can't have a snake that can add. Happy snakes are not purple. Let's see. If we have a happy snake, it can add. If it can add, if it can't subtract, then it can't add. Which means that our snake must not be purple, because if it's not purple, then it can't subtract. And if it can't subtract, it can't add. And if it is happy, then it can add. So that's a contradiction. Because if a snake is purple, it cannot add. And if a snake is happy, it can add. And it can't be both things at the same time. So happy snakes are not purple, which gives us the answer choice of D. Problem number 8. When a student multiplied the number 66 by the repeating decimal 1.AB or 1.AB repeated, where A and B are digits, he did not notice the notation and just multiplied 66 times 1.AB. Later he found that his answer is 0.5 less than the correct answer. What is the 2-digit number AB? Okay, so notice that the 1 is common to both the numbers, so you can just forget about the 1. So now this first number, AB repeated, we will quickly prove why it's what it is, but you can actually research this more, and I'll leave a link to the actual explanation of this in the description below. But this is just AB over 99, and that's because if we have a number, AB recurring, or to write it better, AB, AB, and AB, if you multiply both sides by 100, so let's say this is some number x. If you multiply both sides by 100, you'll get 100x is equal to AB point AB recurring. So it doesn't change the thing after the decimal. And this thing after the decimal, we already established is equal to x. So this is AB plus x. AB plus x. Now we can subtract x from both sides to get 99x equals AB. Or that x is equal to AB over 99, where AB is the two-digit number with first digit A and second digit B. So this number right here, we already subtracted the 1, so this is just AB over 99 times 66. And this is 0.5 greater than just multiplying 66 by point AB. So we can subtract 0.5 from this to get AB over 100. Because a normal two-digit number, you can just multiply it by 100 times 66. So now this simplifies a bit. Both of these have factors of 33. And both of these have a factor of 2. So now the best way to proceed here would be to just check the answer choices. You can also solve this. That would not be the best way. That would be a way to do it, but probably not the fastest. During real tests, you might just want to plug in your answer choices to see what makes sense. And we'll start with D, since we know that E is the answer, so just to save us some guessing work. But during the real test, it's usually considered good to start with the letter C. So we'll start with D, which would give us 60 times 2 divided by 3, which is 40 minus 0.5 is equal to AB over 50, so 60 over 50 times 33, which is 6/5 times 33, or 198 divided by 5, which would give us an answer of 195 plus 3/5. So 195 plus 3/5, 195 is divisible by 5, and 3/5 would make the number end in 0.6. But this number is 39.5. And a number that ends in 0.5 and a number that ends in 0.6 cannot have a difference of 0.5 in between them, regardless of the number before the decimal place. So now let's try 75. 75 over 2/3, which would give us 50, minus 0.5 is equal to 75 over 50, so which is 3 over 2 times 33. 3 over 2 times 33. 3 over 2 times 33 gives us 99 over 2. So now this left side is 49.5. And this right side is also 49.5. So this is equal, and our answer is 75. Problem number 9. What is the least possible value of xy minus 1 squared plus x plus y squared for real numbers x and y? And I gotta admit, this problem sort of tricked me when I first looked at it on the test. But what you can do is actually expand both of these expressions, and a lot of the terms will beautifully cancel out. So this first term, and you can use FOIL, or you should know that a plus b squared in general is equal to a squared plus 2ab plus b squared. We won't prove this formula here, but there's a lot of beautiful ways to prove this. So xy squared, x squared times y squared, minus 2xy plus 1, and then moving on to the second term, plus x squared plus 2xy plus y squared. Now notice that this 2xy cancels out, and we get x squared plus y squared plus 1 plus x squared plus y squared. So here a bit of experience might help. What you can notice is that this factors as x squared plus 1 times y squared plus 1. Because the x squared y squared gives us this first term, the x squared times the 1 gives us this x squared, and the y squared times 1 gives us the y squared, and finally the 1 times 1 gives us this plus 1. Now, an important rule in mathematics, and think about why this might be true, is that any perfect square at its minimum is either equal to 0 or greater than 0. If you want the square root of a negative number, it would be imaginary, but no real number has that condition. So the minimum of this value is 0. And in that case, this would be plus 1. So both of these numbers are positive. And when you're multiplying two positive numbers, to minimize the product, you just want to minimize both the terms. So we get 0 plus 1 here and 0 plus 1 here at the minimum. So this would be 1 times 1, or 1 as our answer. And this happens when both x and y are equal to 0. Problem number 10. Which of the following is equivalent to this expression right here? Now here we use a very clever manipulation called the difference of squares. First, just to make it a bit more obvious how you could see this, is we rewrite everything but with the reverse order. So we get 3 over 64 minus plus 2 to the 64 multiplied by 3 to the 32nd power plus 2 to the power 3 to the power of 16 plus 2 to the power of 16. And notice that I'm trying to write the 3 first, and there's a particular reason for that. Some of you might already see where I'm going with this. 8 to the 4 plus 2 to the 4 and just scooching this a bit here, we get 3 squared plus 2 squared, and then 3 plus 2. So that power would be 1. And now I'm going to add a term, guys. And this is very important to understand, and this is the key insight that you need. I'm going to add the term 3 minus 2. Now, 3 minus 2 is just 1, and if you multiply by an expression by 1, it doesn't actually change the value of the expression. So this is allowed. Now, this is just a difference of squares. The difference of squares states that a minus b times a plus b gives us a squared minus b squared. And the reason is, if you multiply a times a, gives us a squared minus ba plus ab minus b squared. And these two terms in the middle cancel out, giving us this expression. And this is what you can use here. 3 plus 2 and 3 minus 2. Here, a is equal to 3 and b is equal to 2. So I'm going to keep on repeatedly doing this, and I'll give it as a challenge to you to figure out what is a and what is b in each expression. So this is just 3 squared minus 2 squared. Now taking this, we get this is just the same thing as 3 to the power 4 minus 2 to the power 4. Now taking this is just the same thing as 3 to the power of 8 minus 2 to the power of 8. And you'll see where I'm going with this. You'll also notice the pattern that whatever term I'm on, the exponents are double. So going all the way here, we'll see that this is equal to 3 to the power of 64 minus 2 to the power of 64. The product of all these. And now multiplying these two, we'll get 3 to the power of 128 minus 2 to the power of 128. And guess what? That is answer choice number C. So that works. Bases. Now, if you don't know how to deal with bases, I have a video on that. It can give you a nice introduction, although an introduction might not be enough for this question. For which of the following integers b is the base b number 2021 in base b minus 221 in base b not divisible by 3? So we'll use the place value system to solve this question. In base b, 2021 is equal to b cubed times 2 plus 0 times b squared plus 2b plus 1. Now this second number, and then notice how similar this is to base 10. In base 10, b is just equal to 10, and that would be our normal place value system. So minus 2b squared minus 2b minus 1. So this 2b cancels out, this 1 cancels out, and we're left with 2b cubed minus 2b squared. And when is this not divisible by 3? So this means 3 is a factor of this. If we put a line through, it means that 3 is not divisible by that. Let's factor this. That might tell us a bit more. Factor out the 2, factor out the b squared term, and you'll be left with something that looks a bit like this. Now, notice that if b is a multiple of 3, then this number is automatically a multiple of 3. So multiples of 3 don't work. What if b is one more than a multiple of 3? Well, if it's one more than a multiple of 3, and then you subtract that one, you have a multiple of 3 again. So this term would give us a multiple of 3 in that case. Well, 7 is one more than a multiple of 3, or more specifically 6, and 4 is one more than a multiple of 3, or more specifically 3. The only answer choice we're left with is 8. And checking it out, 64 times 2, that doesn't have any factors of 3. And 8 minus 1, that's 7. That doesn't have any factor of 3. So that works. Problem number 12. Two right circular cones with vertices facing down, as shown in the figure below, contain the same amount of liquid. The radii of the tops of the liquid surfaces are 3 centimeters and 6 centimeters. Into each cone is dropped a spherical marble of radius 1 centimeter, which sinks to the bottom and is completely submerged without spilling any liquid. What is the ratio of the rise of the liquid level in the narrow cone to the rise of the liquid level in the wide cone? Okay, so the volume of the first cone is given to be whatever the current height is. Let's say it's h1, and whatever the area of this face is, which is 3 times 3 times pi, 9 pi times h1. And to find the volume of a cone, you always have to divide by 3, is equal to volume. Let's just call that V. Now for the second one, we get, in a similar way, 36 pi squaring the 6 divided by 3 times h2 is equal to V. Well, we can use a clear substitution technique here. Since both the V's are equal to each other, their counterparts, or whatever they're equal to, are equal to each other. So 9 pi times h1 over 3 is equal to 36 pi times 3 times h2. This 3 cancels out, this 9 cancels out to leave a 4 here, and this pi cancels out. So we're left with h1 is equal to 4 times h2. What does that tell us? That tells us that this height, one of the heights, the height of the second thing to be more specific, is 1/4 of the height of this first cone. Now, whatever we add, and this is enough for the test taking conditions, although you might want to prove it more rigorously outside of the test. Whenever we add the same amount of volume, we expect that the height of the cone and the height of the cones should increase in the same volume, or in the same ratio. So if we add this volume 2 to both of these, the height will increase proportionally, where h2, whatever it increases by, h1 will increase 4 times more. And notice that the volume of the marbles remains the same for both of them. So that's basically this condition. And thus our ratio would stay the same, 4 to 1. Problem number 13. Number 13. What is the volume of tetrahedron ABCD with edge lengths A, B equals 2, AC equals 3, AD equals 4, BC equals the square root of 13, BD equals 2 times the square root of 5, and CD equals 5. So now, I sort of cheated a bit here by drawing a diagram beforehand, but this isn't anything complicated and can easily be drawn during the actual test. But one thing that you must notice is that we notice some Pythagorean triples, or more specifically, triples where two of the numbers, when we square them and add them up, we get the third number squared, which means that it might be a right triangle. For example, AC, AD, and CD, 3, 4, and 5. That's one of the most famous Pythagorean triples, because 3 squared plus 4 squared equals 5 squared. So that is a right triangle. Similarly, we notice that AB plus AC gives us BC squared, so AB squared plus AC squared gives us BC squared. And we'll notice other patterns. So let's start drawing it. A, B, C, D. So now that we have A, B, C, D, we can label the sides, and what we'll notice is that ABD is a right triangle, ACD is a right triangle, and ACB is a right triangle. Now this is very, very helpful for us. And the reason being is that what we can do with this is what we notice is that we have 3 right triangles, and this is basically the same as the area of or the volume of a tetrahedron is finding the area of the base and multiplying it by the height and dividing by 3. And this is very easy for us now that we have so many right angles. So the bottom is just a right triangle ABD with edge length 2, 4, with legs 2 and 4, and hypotenuse 2 square root 5, and you can double check that if you want. And so the area of that is 2 times 4 divided by 2, since it's a triangle, which gives us 4. Now this height is just going to be AC, since that's a right triangle. AC, the problem tells us, is equal to 3. And we multiply by 3. Now since a tetrahedron is just basically a pyramid, we have to divide by 3. 4 times 3 divided by 3 just gives us 4, which is our answer of C. Problem number 14. All the roots of polynomials z to the power of 6 minus 10 times z to the power of 5 plus a times z to the power of 4 plus b times z cubed plus c times z squared plus d times z plus 16 are positive integers. So underline that because that seems important. Possibly repeated. What is the value of b? Okay, so the fact that they don't give us the value of a, c, and d might be a hint that maybe those values don't matter. And when do those values not matter? Well, they give us this condition that they're positive integers, so that constrains it a lot. Well, when do those values not matter? That would be in Vieta's formula, which basically tells us a lot of information about the roots. More specifically, it tells us that the product of all the roots is going to be 16, because that's the last constant number. And the sum of all the roots is going to be 10. Notice that it says negative 10, but Vieta follows a negative pattern. So 16 would be positive, negative, positive, negative, positive, negative, given that all the roots are positive. So we know that the sum of the 6 roots, I'll just call it A1 plus A2 plus A3 plus A4 plus A5 plus A6 is equal to 10. And multiplying all of these out, so A1 to 6, which is basically shorthand for that, is equal to 16. So now you can just guess a few roots. If you try 4, 4, 1, 1, 1, 1, the sum is going to be too much. The sum is going to be 12, but the product's going to be just right. Maybe we can try 2, 2, 2, 2, 1, 1. That would give us a 2 plus 2, 4 plus 4, 8 plus 2, 10. So that works. So our roots are 2, 2, 2, 2, 1, and 1. Now we sort of have to do a bit of casework to find b. Notice one very important thing about b. b is just basically just like how this is a sum of all the roots and this is a sum of all pairwise roots, this is the sum of all the possible triplets of the roots, their product, the product of each triplet, and finding that sum. So let's say we have 1 1 in this product. If we have 1 1 in this product, so there's 2 ways of choosing the 1. Remember, order doesn't matter. And 4 choose 2 ways of choosing the other 2s. So that gives us 12. And the product of that would be 2 times 2 times 1. Or more specifically, 48. Now, what if we have both of the 1s? Then we have 1 choice for the ones that we're taking, since there's 2 1s and we're taking both of them. And 4 choices for the 2 that we're taking. So that's 4 times 2. Because the value of that product is 8. Is 2 times 1 times 1, 2. And 4 times 2 would give us 8. Now finally, what if we have 0 1s? In that case, we have 3 2s, and there's 4 choose 3 ways of picking the 3 2s. Or more specifically, picking the 2 that we're not taking. And so there's 4 ways of that, and the product of this is 2 times 2 times 2, which gives us 8, or 32. Now adding these up, we get 70, 80, 88. but 88 is not one of the answer choices. Well, remember that pattern from earlier? Well, it tells us that D, B, and this negative 10 are all going to be negative. So our answer would actually be the negative version of 88, which would be negative 88, giving us our answer of A. Problem number 15. Values for A, B, C, and D are to be selected from the set 1, 2, 3, 4, 5, and 6 without replacement, which means that no two letters will have the same value. How many ways are there to make such choices so that the two curves y equals ax squared plus bx and y equals cx squared plus d intersect? The order in which the curves are listed does not matter. For example, the choices a equals 3, b equals 2, c equals 4, d equals 1 is considered the same as a equals 4, b equals 1, c equals 3, d equals 2. So notice that for each case, there's actually one more case that we can get by switching it around, but that is not allowed. So if order did not matter, and then we divided those number of cases by 2, we would get the actual number of cases. So let's continue. We know that y is equal to ax squared plus b and y is equal to cx squared plus d. Well, if they're both equal to y, we can set them equal to each other. We have a x squared plus b equals c x squared plus d. Grouping like terms, we get ax squared minus cx squared equals d minus b. Now, ax squared gets factored out and we're left with a minus c on the left side and d minus b. Dividing both sides by a minus c to isolate the x squared term, we get d minus b over a minus c. Now, notice that x squared is always either equal to 0 or greater than 0, and we talked about this earlier in this video. But it can't be equal to 0, because in that case d and b would be equal to each other, which is not allowed because it's without replacement. So this thing on the right hand side, this expression, is positive. A fraction is only positive when both the numerator and the denominator are positive, or they're both negative. So let's proceed with casework. Now, for D and B, we have 6 times 5 values, because there are 6 values for D and 5 values for B. Now we have 4 times 3 values for A times C, but only half of them will work. Out of these 4 times 3, if D is greater than B, then we need to make sure that A is greater than C, which only happens with 50% chance. And if B is greater than D, in which case the top is negative, we need C to be greater than A, which also happens with 50% chance. So we divide this by 2. Finally, we multiply by the 1/2 that we mentioned here because order does not matter. Let's multiply this out. We get 6 times 5 times 3, which gives us 30 times 3, or 90. Number 16. In the following list of numbers, the integer n appears n times in the list for 1 is less than or equal to n is less than or equal to 200. What is the median of the number in the list? Of the numbers in the list. Now, to find the total numbers of the total number of numbers in this list, you have to notice that there's 1 1, 2 2s, 3 3s, or basically it's just the sum of 1 plus 2 plus 3 all the way to n. And the formula for this is n times n plus 1 divided by 2. Applying it to 200, since that's the value of n in this case, get 200 times 201 divided by 2. 200 divided by 2 is just 100, so we get 20100. Dividing by 2 to find the median value, we get 10050 and 10051. Like, our median will be the average of these two terms. So let's go down a bit. Now, a good guess to start out would be 150, and the reason for that is if it's too high, if it's higher than these numbers, we will know that D and E both don't work. We already know that A doesn't work because A is at the 50% mark, and the problem with that is the first 100 digits appear way less than the second 100 digits, and think about why that's true. So we can already cross that out, but let's start with 150. 150 times 151 divided by 2. So now this would give us 75. Instead of doing 75, we can do 151 times 100 plus this divided by 2, since that's 100 divided by 2 equals 50. Think about why that makes sense. So that would give us 7550. And we divide this by 2. So this is 22,650 divided by 2, or 11325. Now 11325. That seems to be, that's more than the numbers that we're looking for. We're looking for these two numbers. So let's try 140. That seems like a good guess. Plus, if it's too low, we can also rule out 134. Now we can rule out D and E since our answer is less than 150 and these numbers are more than 150. 140 times 141 divided by 2 is 70 times 141, or 1410 times 7, which would give us 98, because 14 times 7 is 98, 70, because 10 times 7 gives us 70. Well, this is less than these numbers, so 140 is too less. 140 is too less, 150 is too much. So that means our answer is between 140 and 150. And the only answer choice that satisfies that is C. So our answer is C for question number 16. Problem number 17. Now I'll admit this was a hard one. Trapezoid ABCD has AB parallel to CD, BC equals CD equals 43, AD is perpendicular to BD, and we let O be the intersection of these diagonals, AC and BD. Let P be the midpoint of BD. Given that OP equals 11, the length AD can be written in the form m times the square root of n, where m and n are positive integers and n is not divisible by the square of any prime. What is m plus n? Now, I did cheat a bit by drawing this diagram a bit in advance, but it should suffice since it's a pretty rough diagram and you should be able to make this during the actual test. Let's draw in this CP all the way to AB just to intersect it. That way now we have OPC as a triangle with 11 as a side, which might help us. Not sure though. So we have this, let's let it equal M. And what we notice is that if we draw in DM, sorry for the bad drawing, we'll have a kite. DMBC is a kite, and the diagonals of a kite are perpendicular. And now we know a lot of things. Notice that P, B, and M are perpendicular. It's similar to D, A, and B. The reason being is it double angle congruence, since angle D and angle P are equal, and angle B is obviously equal to angle B. And since BP over BD is 1 over 2, this is equal to this. Let's write it down just to make it a bit more concrete. So BP over BD is equal to 1 over 2. So then BM over AM is also equal to 1 over 2. Which tells us that 2 times BM equals AM. And since AM is BM plus another value, we can subtract BM to get BM is AM. Instead of this AM though, we should have an AB here. And an AM right here. Okay, so that helps us out quite a bit. But one thing that we should notice is that MP is also half of AD. So if we let this equal X, this is 2X. Now we already know that everything here is perpendicular in the diagonals of this kite. We have that angle AOD is equal to angle POC. We also have that angle P is equal to angle D since they're both right triangles. angle AOD is equal to angle POC because they're vertical angles, which means that they're equal. So we have that triangle AOD is similar to triangle COP by double angle similarity. That gives us DO over 11, or DO over PO, that's where I got the 11 from, is equal to AD over CP. AD over CP. Now notice that since this is a kite, MC is the diagonal that's being bisected. So this is the same as AD over MP. We already know that AD over MP is equal to 2, so DO over 11 is equal to 2. And remember, AD is 2x and MP is x. That's where I got my 2 from. So DO is equal to 22. Now we can apply the Pythagorean theorem. AD is equal to AB squared minus BD squared. So we have the right triangle ABD. So AD is equal to AB squared minus BD squared, and we take the square root of this whole thing. So now AB is obviously equal to 86 because MB is 43 and this is 43. And think about why that is true. So this is the square root of 86 squared minus the value of BD squared. Now, since DO is equal to 22 and OP is equal to 11, DP is equal to 33, and since P is the midpoint, PB is also equal to 33. So that total is 66, so 66 squared. Now, using the difference of squares on this, you get square root of 20 times the square root of 86 plus 66, which would give us 140 plus 12, or 152. Now we can take out 16 out of this, and when you take 16 out of a square root, it would become a 4. So let's divide both terms by 4 to get 4 square root of 5 times 152 divided by 4, which would give us 3 times 8. This is 4 times the square root of 190. Now we can't take out any more terms inside the square root, so our answer is 4 times the square root of 190. Adding up m plus n, or 4 plus 190, we get our answer as 194. Let's move to question number 2. Question number 2 was super interesting and probably my favorite question on the test. Question number 18. Let f be a function defined on the set of positive rational numbers with the property that f of a times b is equal to f of a plus f of b for all positive rational numbers a and b. Suppose that f also has the property that f of p equals p for every prime number p. For which of the following numbers x is f of x less than 0? So now let's play around with this function a bit. Notice that f of 3 times 2 is just f of 3. So 3 times 2 is 6. F of 6 is equal to f of 3 times 2 is equal to f of 3 plus f of 2. F of 3 is just 3. F of 2 is just 2. So this gives us 5. So f of 6 is just equal to 5. Now, what if we have a prime, f of p, and we multiply it by 1? Well, now this is the same thing as f of p plus f of 1. Now this is just f of p. Subtracting f of p from both sides, we get that 0 is equal to f of 1. So f of 1 is equal to 0. That is going to help us out a lot. Because now what this tells us is f of p times 1 over p, which is just f of 1. Let me write it here. F of 1 equals f of p times 1 over p is equal to f of p, and where p is any prime, plus f over f of 1 over p. So we're saying that 0 is equal to f of p, which is p, plus f of 1 minus p. 1 over p. So minus p is equal to f of 1 over p. And this will help us a lot in this problem. So now what we do right now is we look at the answer choices and try testing them. The first one that I tried was E, and the reason being is that all of the answer choices seem to be less than 1, and it's out of D and E. I just randomly went with E. So we'll go with D here just to show what happens then, and then we'll take a look at E. So we just tried the different answer choices. Let's look at f of 7, 6. Now we have to play around a bit. It won't just come to you immediately. You have to play around a bit to see what happens in a case like this. Now this is f of 7 times 1 over 2 times 1 over 3. This formula basically generalizes to more things. F of A times B times C is equal to f of A plus f of B plus f of C. And that is very important. And you can see why that works. Basically, what you can do is group AB together, and that'll be f of AB plus f of C, and then expand f of AB, which will give you this formula. So this is just f of 7, which is 7 minus 2, since 1/2 is just minus 2 using this formula that we learned here, since 2 is prime, minus 3, which gives us 2. So this is positive. That works. Now let's try f of 25 over 11. This is f of 25 minus f of 1 over 11 plus f of 1 over 11. Now f of 25 is just f of 5 plus f of 5. And since 5 is a prime number, that gives us 10. And f of 1 over 11 is just minus 11, which is negative 1. And since this gives us a negative number, we get E. Question number 19. The area of the region bounded by the graph of x squared plus y squared equals 3 times the absolute value of x minus y plus 3 times the absolute value of x plus y. Now, a very important thing to note in this problem right here, the total area is m plus n times pi, where m and n are integers. What is m plus n? So a very important thing to note here is that the solutions are the same for plus or minus x and plus or minus y. And the reason being that since we're dealing with absolute value and square roots, the values don't change. Even the absolute value won't change, even though it looks a bit weird because of the different absolute values. So it suffices to just look at one possible quadrant. If we look at quadrant number 1, that would be the easiest. That means that both x and y are positive. So there's two possible cases. Either x is greater than y. If x is greater than y, we get x squared plus y squared is equal to 3x minus 3y, since x minus y would then be positive, plus x plus y is always positive if x and y are both positive. So that will give us 3x plus 3y. This 3y would cancel out, and we would get x squared plus y squared equals 6x. Subtracting 6x from both sides, we would get x squared plus minus 6x plus y squared equals 0. Factoring this, for completing the square, which is a very important technique for tests like these, and adding 9 to both sides, we get this expression. Now this is just the equation of a circle, and you can watch our video on that if you want to know more about that. But that's the equation of a circle with a center of 3, 0, and a radius, so let me write this 9 as 3 squared, and a radius of 3. So let's try graphing this. Let's take a look here. So we have this line right here, and we're assuming that x is greater than y. So what we have is, if we draw 3 here, 3 here, we would have this semicircle since we're only looking at quadrant 1, but since we have this line here, basically we have something that looks a bit like this. And this is a quarter circle with this triangle area where this is 3, this is 6. So now what if you replaced x and y? So what if y is y is greater than or equal to x? In this case, just notice that it would be flipped. So instead of x minus y, this would be y minus x. Since it would be negative, so we multiply by -1. And you could multiply all this out, but what you notice is that the value of x and y is just basically switched. So we do the switcheroo here, and with y minus 3 squared plus x squared equals 3 squared. So it's a circle with center 0, 3, and it's basically done in the same way. And we have another quarter circle with a square. So this quarter circle is 3 squared times pi divided by 4, since it's a quarter circle, 9 pi over 4. We multiply by 2 since there's 2 of these, which gives us 9 pi over 2. That square just has a side length of 3, and 3 times 3 gives us 9. So our answer is 9 pi over 2 plus 9. Now remember, there are 4 quadrants, so you need to multiply this by 4 to get 18 pi plus 36. Now we have to find the sum of n plus n, which would be 36 plus 18, which would give us an answer of 54. Now problem number 20. In how many ways can the sequence 1, 2, 3, 4, 5 be arranged so that no 3 consecutive terms are increasing and no 3 consecutive terms are decreasing? Now notice that by symmetry, it's enough to count the number of sequences that are increasing. Because if you subtract, for example, say we have a valid sequence like this. Now we can find the opposite sequence by subtracting each term from 6 to get 5, 4, 3, 2, and 1. And that's how that would work. So now let's try solving this problem. We can use a bit of casework. So we're asked so that no 3 consecutive terms are increasing. Well, let's say the first term is A and the second term increases to B. In this case, the third term cannot be C. Because if the third term is C, then A cannot be greater than A and B, because in that case, A, B, and C are 3 consecutive terms in increasing order. So if we let some number here, we have to have greater than x, then less than x, then greater than x, and then less than x. And the reason for that is this is the only possible arrangement that makes sure that nothing appears that has more 3 or more consecutive terms that are increasing or decreasing. So we're assuming that this is greater, but we can also assume that it's less, but like we said, that's already symmetric, so it's enough to just count the number of variations where it's greater. So now we can do some casework. Since the numbers are pretty small, where the maximum is 44, and since it's symmetric, the maximum number of cases we'll have is 22, and the minimum is 5. So it shouldn't be too bad. So we start with x is 1. So now maybe we have a 2 here. But now whatever term we'll have here, it'll be increasing, so that's not allowed. So maybe we have a 3 here. Now the only term that fits here is 2. We need a term that's greater, which would be 5, and we would get a 4 here. Or we could put a 4 here, and now we have 2 choices here. First, we can put a 2 here, in which case we would need to have a 5 here and a 3 here. We can put a 1, 4, and a 3, in which case we would still need to have a 5 here, but the 2 moves here. Now finally we could have 1, 5, 2, in which case basically you'll notice that most of the times the last 2 terms only have 1 possible combination. So in this case we have 4, 3, Or we could have a 1, 5, and 3, in which case it would be 4, comma 2. We could have a 1, 5, 4, and now whatever we put here is going to be less than the 4, so we can't have that. We can now move to the next number, 2. So say we have a 3 here. Well, we need to have a 1 here, a 5 here, and a 4. That's the only arrangement that works. We might also have a 2. Oops. So we might have a 2, a 4, and now we have two choices here. First, we could have a 1, 5, and 3, or we could have a 2, 4, 1, 2, 4, 3, 5, 1. Finally, we could have 2, comma 5, and now you could have a 1, 4, 3 here, a 2, 5, 3, 4, 1 here, and you can't have a 4 because then all the terms after that would be less. We're almost done with the casework. We move to 3. Now we have 3, 4, and a 1 here, in which case this would be 5, comma 2. Or we could have a 3, a 4, and a 2 here, in which case this would be 5, comma 1. Or we could have 3 and a 5 here. Now we could put a 1 here, in which case there would be a 4 here and a 2 here. Or we could have a 2 here, in which case there would be a 4 and a 1 here. Once again, we can't have the 4 there because then all the terms after that will not be greater. So we're done with that case. Finally, we could have a 4 here, a 5 here, and a 1. In this case, 3, comma 2 works. We can also have 4, comma 5, comma 3. But then after that, we won't have any greater terms, so we would need 2, 3, and 1. And we can't have 5 as the first term since there's nothing that's greater than a 5. So adding up all of these cases, we get 5 plus 5 plus 4 plus 2. So the casework is a bit extensive, but it's one of the easier ways to do this problem on the test. Afterwards, there might be an easier way to solve it, but on the test, this was probably the easiest way to solve it. So this gives us 5 plus 5 plus 4 plus 2, or 16 total ways. Now, our answer is not 16, and that's not even an answer choice. We have to multiply by 2 since we also have to consider the terms where they're decreasing. So this term would be less, greater, less, greater, in that pattern. So they're decreasing first instead of increasing. And that would give us an answer of 32. Now we can finally move to problem number 21. Number 21. Let A, B, C, D, E, F be an equilateral hexagon. That basically means that all the angles of the hexagon are equal. The lines AB, CD, and EF determine a triangle with area 192 times the square root of 3, and the lines BC, DE, and FA determine a triangle with area 324 times the square root of 3. The perimeter of hexagon ABCDEF can be expressed as m plus n times the square root of p, where m, n, and p are positive integers and p is not divisible by the square of any prime. What is m plus n plus p? Now a hexagon, where all the angles are equal, has each angle of 120 degrees. And you can find that by multiplying n minus 2 times 180, that's the formula to find the number of degrees in a shape, and divide that by n. In this case, n would be 6. So we get 4 times 180 divided by 6, which would give us 120. A quick check. But it's not like a regular hexagon where each side is equal. And I'm going to draw the shape as an approximate sketch. So let's label it A, B, C, D, E, and F. Now the lines AB, EF, and CD. So let's draw it out. Determine a triangle with area 192 times the square root of 3. By the way, we sort of suspect that since there are two different type of triangles, we probably have two different type of side lengths. That sort of seems likely. So for now, I'm gonna label AB as X and AF as Y. This might not be the case, but we'll assume that it is the case. And we'll prove it later if it is true. It also tells us that BC, DE, and FA also determine a triangle. BC, DE, and FA. So drawing this, we get this triangle. And the perimeter of hexagon ABCDEF can be expressed as m plus n times the square root of p. So now, since this is 120 degrees for each angle, this is 60 degrees. Same thing, this is 60 degrees. And since the total sum of the degrees of a triangle is 60 degrees, we have 6 equilateral triangles. Now, I won't label all of them, but most of them I have labeled. But this tells us something very big. These big triangles that we've drawn, since they each have angles of 60 degrees, they're equilateral. So now we can apply the sum of an equilateral triangle formula, which is s squared times the square root of 3 divided by 4, where s is the side length. So for triangle number 1, we have s squared, square root of 3, divided by 4 gives us 192 square root 3. Square root 3 cancels out, s squared gives us 192 times 4, and s gives us 2 times the square root of 192. So the square root of 192 we can divide by 4 to get 4 d8. We can divide by 4 again to get 12, and we can divide by 4 again to get 3. Basically, what you'll notice is that 192 is divisible by 64, which is the square of 8. So let's apply that, and we'll get 2 times 8 times the square root of 3, or 16 times the square root of 3. Same thing for the other triangle, and we get s squared, and this is a different s, so let me label it as s1 squared. Square root of 3 over 4 equals 324. Square root 3. Square root 3 cancels out, and we get s1 squared equals 4 times 324. The square root of both sides would be 2 times 18, because the square root of 324 is 18. So s1 is just equal to 36. Now, let's try solving this problem. Since we know that these angles are 60 degrees, this is y and this is y, since it's also equilateral triangle. Similarly, this is y, this is x, and just labeling it in a similar way. Y, x, and x. So now what are we trying to find? We're trying to find the perimeter of this hexagon. That's just x plus x plus x, y plus y plus y, or 3x plus 3y. Now we know that y plus x plus y is equal to one of these two side lengths. So 2y plus x, let's say it's equal to 16 square root 3. Doesn't matter. You don't even have to check. And the other side length is 2x plus y. X, y, and x. So x, y, and x. So that gives us y plus 2x is equal to the other side length. And it doesn't even matter if these two should be reversed for this problem. And you'll see why in a second. Now we could solve for the values of x and y here. But notice what? If we add up both of these, we get that 3y is equal to 3x. And that's exactly what we're trying to find. So this gives us 16 square root 3 plus 36. Adding all of this up, we get 36 plus 16, which gives us 52, plus 3, which gives us 55. So it doesn't even matter what order it's in, but our original assumption that x and y were the two side lengths of the hexagon is correct. Let's now solve problem number 22. Problem number 22. Hiram's algebra notes are 50 pages long and are printed on 25 sheets of paper. The first sheet contains pages 1 and 2, the second sheet contains pages 3 and 4, and so on. One day, he leaves his notes on the table before leaving for lunch, and his roommate decides to borrow some pages from the middle of the notes. When Hiram comes back, he discovers that his roommate has taken a consecutive set of sheets from the notes and that the average or the mean of the page numbers on all the remaining sheets is exactly 19. How many sheets were borrowed? Now let's find the total sum of the sheets before we do anything else. Applying that formula that we learned about earlier, we get 50 times 51 divided by 2, which is 510 divided by 4, which gives us 1, 2, 7, D5. So 1275. So now, let's let x be the number of the first page he borrowed and let n be the number of sheets. So now to find the average, we get 1275 minus n times, so it's an arithmetic sequence, 2x plus 2n minus 1. And let me explain this a bit more. So this is an arithmetic sequence, so the pages that he took out, with the first page being x, the second page being x plus 1, all the way to the fact x plus 2n minus 1. And it's 2n because n is the number of sheets, not the number of pages, so we have to multiply by 2. So it goes all the way to x plus 2n minus 1. Now he took out n sheets, so that's 2n pages, and since we're supposed to divide in the arithmetic sequence formula, we can just multiply by n instead of multiplying by 2n and dividing by 2, which is where we get this number from. Now if we divide by the total number of remaining pages, which is 50 minus the number of sheets he borrowed times 2, we should get 19, as the problem states. Now we can multiply both sides by 50 minus 2n. So we can multiply both sides by 50 minus 2n to get 1275 minus n times 2x plus 2n plus minus 1, which equals 950 minus 38n. Now grouping like terms, so I bring the 950 all the way to the left hand side. 1275 minus 950 gives us 325. And adding this here and subtracting 38, so the 38 would go inside the parentheses. We get n times 2x plus 2n minus 1 minus 38, or 2x plus 2n minus 39. Now this is easily solvable, and the way that you can do that is you can look at the factors of 325, and basically n could be one of those factors and x could be the other factor, so this would be the other factor. We didn't proceed that way. Instead, we took a look at the answer choices, and starting all the way from the left, you can start plugging them in, and we'll save you the time. You'll realize that B13 works. If you plug in 13 for n, you'll get an odd number for x, which is what you need, and no other number satisfies that. So the answer is B. Problem number 23, a very good problem on this test. Frida, the frog, begins a sequence of hops on a 3x3 grid of squares. moving one square on each hop and choosing at random the direction of each hop, up, down, left, or right. She does not hop diagonally. When the direction of a hop would take Frida off the grid, she wraps around and jumps to the opposite edge. For example, if Frida begins in the center square and makes 2 hops up, the first hop would place her in the top row middle square, and the second hop would cause Frida to jump to the opposite edge, landing in the bottom row middle square. Suppose Frida starts from the center square, makes at most 4 hops at random, and stops hopping if she lands on a corner square. What is the probability that she reaches a corner square on one of the 4 hops? Now, even in the 2020 AMC 10A, we had a problem about a jumping frog, so AMC 10 probably really loves jumping frogs. But let's start by drawing a grid. And what you'll notice is that regardless of where the first arrangement takes the frog, it'll be one of these middle squares. So either this square, this square, or this square. And it doesn't matter. With probability 1, the frog will land in one of those 4 squares. Okay, so let's assume this square. And it doesn't matter which square. Now with a 1/2 chance, we'll go to a corner square, or 2/4, which is 1/2. With a 1/4 chance, we'll go forward and actually come back to this square. And here, we can do some casework. So let's look at the case where instead of going back here, we decide to go forward and come back here. One thing that you should note is that you can add up all these probabilities since they're independent probabilities, and you can add them up and that would still suffice to get the answer. So we already looked at the case where the frog went here and then went left or right. So with probability 1/2, she'll just go into a corner square on her second move and be done. With a probability of 1/4, she'll land back to one of these middle edge squares. Here, once again, with a probability of 1/2, she'll land in one of the corner squares. So that's 1/2 times 1/4, which gives us 1/8. Plus, she might go here. But if she goes here, that's already 1, 2, and 3 moves. And there's nowhere on the 4th move that the frog can go to a corner square from here. So with 1/4 chance, they might go back. And then once again, on that move, you have a 1/2 chance of picking a corner square. And you have to pick one there because that's your 4th move. Otherwise, that's it for her. So we have 1/4 times 1/4 times 1/2, which gives us 1/32. You just put parentheses around that. Okay, so we looked at that case. Now, the second case that we have to look at is instead, what if we go here and then we go back? So what happens if we decide to go back? If we decide to go back, that's 1/4 probability. Then whichever way we go, once again, we're on case number 1, we'll land in one of the squares. Maybe we'll pick this one or that one. And there, once again, with probability 1/2, we'll go into one of these squares. And that's it. After that, we've already accomplished our 4 steps. So that's a probability of 1/4 times 1/2, or 1/8. So we have 1/2 plus 1/8 plus 1/8 plus 1/32. Now this is 1/2 plus 1/4, which is 3/4, and adding 1/32 to that gives us 24/32 plus 1/32, or 25/32. This is definitely one of the easier number 23s on the AMC 10 test. Problem number 24. The interior of a quad is bounded by the graphs of x plus ay squared equals 4a squared and ax minus y squared equals a squared, where a is a positive real number. What is the area of this region in terms of a, valid for all a greater than 0? The best way to solve this problem is to assume different values of a. Now there might be a more rigorous way, but the most practical way is probably plugging values of a. We decided to plug in a equals 2. That gives us x plus 2y equals, or squared equals 4 times 4 or 16. And we also get that 2x minus y squared equals 4. Now, if you start graphing this, you'll see that it's not that hard to graph and the values aren't that big. In fact, all the intersections happen pretty quickly. And we already graphed it for you right here. So the points of intersection are 2, 0, 0, 2, I mean. Then we have 1.6, so then we have 0, negative 2. After that, we have the values 1.6, 1.2, and the points negative 1.6, negative 1.2. Which makes sense. If xy is a solution, then negative x, negative y is also a solution. In this case, this is just a right triangle. Right here, an approximate right triangle. And since this point is 0, 2, and this point is 1.6, 1.2, it's a right triangle with side length 1.6 and 0.8. Now similarly, this is a right triangle. This has side length of 1.2 plus 2, so 3.2 and 1.6. Now, this is 0.8, this is 1.6. Squaring 0.8, we get 0.64. Squaring 1.6, we get 2.56. This would give us 3.2. So this is the square root of 3.2, and we're not going to simplify that or anything because we'll see that it actually cancels out. Now here we have 1.6 and 3.2. So once again, it's just going to be 3.2 squared, which gives us 10.24, plus 1.6 squared, which gives us 2.56. Adding this up, we get 0, 1, 8, 10, 12.8. So the square root of 12.8. Now, what happens if we multiply 12.8 times 3? If we multiply 12.8 times 3, that's the area of this triangle. 12.8 times 3.2. Rewriting 128 times 32, 10 times 10. Now we have a lot of things that cancel out, but more specifically, 128 times 32 is 4096. 4096 divided by 10 times 10 gives us 100, which gives us 40.96. So 40.96, now you might recognize that this is actually a perfect square. It's the square, so 4096 is the square of 64. So this would be the square of 6.4. So now you might recognize this Pythagorean triple, but it's okay. You can bash it out if you didn't. So the area of this is 6.4 or 32.5. Now, let's plug in our answer choices for 2. If we plug in 2 in this first choice, we get 2 squared, that's 32, plus 2 plus 1, that's 3 squared, 32 over 9. That does not seem to work. Now, what if we plug in here? We get 2 times 4, 8 over 2 plus 1, 3. That doesn't work either. What about here? 2 times 8, 16 over 2 plus 1, 3. No. What about here? 8 times a squared, which is 32, plus a squared, which is 2 times 2, 4 plus 1. That's 5. That's the answer we're looking for. Let's just quickly double check this last one. This one is missing that a on the top. So we have 8 times 8, so 16 over 5. Our answer is thus D. Now there might be better ways to solve this problem, but this is the go-to way during a problem, and it's a technique that we use to solve this problem without actually solving the problem fully, which is very helpful in tests sometimes. One of the many meta-induction techniques. Okay, let's solve problem number 25. How many ways are there to place 3 indistinguishable red chips, 3 indistinguishable blue chips, and 3 non-different green chips in the squares of a 3x3 grid so that no 2 chips of the same color are directly adjacent to each other, either vertically or horizontally? Okay, we'll proceed with casework here. Let me draw grids for this one. Let's just start out with drawing 2 grids for this one. For this problem, we have 2 different orientations that we can have. First of all, I'm just going to assume that the colors are 1, 2, and 3, instead of red, blue, and green. And at the end, we have 3 factorial ways, or 3 times 2 ways, to pick the colors 1, 2, and 3, since we have 3 choices for color 1 and 2 choices for color 2. So we can just multiply our answer time by 6 at the end. And I'll just write this here just so I remember. And that sort of makes sense since all of the answer choices are multiples of 6. 1 goes here. And let's assume that this first arrangement is like this. If it's like this, now let's assume color 2 goes here. It's the same as saying color 3 goes here, because we're assuming that these colors are fixed. So this arrangement is fixed. Now here, since we only have 2s and 3s left, the 3 must go here, the 2 must go here. Now we have to put 2 3s here, so we can't put a 3 here because then there's no 3s allowed here, which would not work. So we put the 3s here and the 2 here. So this is one arrangement, but we could have also put the 1s on the other diagonal, so that instead of this arrangement, it would be 1, 1, 1, and we would still do the same thing. Here we would still put the 2, 3, 2, 3, 3, 2. So there's times 2 of these arrangements. The second type of arrangement we could have for the 1s is 1, 1, 1. For this arrangement, what we can do is, let's say we have 2 here. Now we can't have a 3 here. We have to have a 3 here. So we must have a 2 here, a 3 here, a 2 here, and a 3. And this is the only possible arrangement that works for this one. Now there's 4 different ways of this, because the 2 1s that are on the same side, we have 4 different sides that we can pick for that. It could be 1, 1 here, or 1, 1 here, or 1, 1 here. So that's times 4. In total, we have 6 possible ways. Multiplying by 6 gives us 36. Since that's the max answer, we can feel extra confident since we didn't miss any cases. Thus, our answer is 36 for number 25, or E. That's it. We just went over all the solutions from the 2021 AMC 10A. If you have a different solution, feel free to comment it down below. Thank you for watching this video. If you liked this video or learned anything from it, let me know by subscribing or commenting below. For more awesome content, check out thepuzzler.com. You'll find amazing articles and free courses there. Thank you.